As requested, let's check Hilbert-Schmidth theorem and some examples of how to solve integral equation by using Hilbert-Schmidth theorem. So here we will prove Hilbert-Schmidth theorem and some how to apply that Hilbert-Schmidth theorem for the integral equation, and in the next video we will see how to solve the integral equation by using Hilbert-Schmidth theorem. So for that I have already written the statement for Hilbert-Schmidth theorem. So Hilbert-Schmidth theorem, it says if a function fx can be written or can be expressed in the form fx equals to integral from a to b kxt ht dt. So in this case, if you have classified this integral equation, then it is a integral equation where your unknown function hx is not outside the integral sign, and this fx is there. Okay, so non-homogeneous Radon integral equation of dash dash kind. So you see what is that dash dash outline. So here let us denote this as equation number 1, where kxt is a symmetric L2 function. It has to be a symmetric L2 function, and ht is any L2 function. So this is the integral equation in the unknown function h. Then this fx can be expressed or expanded in the absolutely and uniformly convergent Fourier series. I hope you have studied already the course on Fourier series and Fourier transformations. So you can express this fx in an absolutely and uniformly convergent Fourier series with respect to the orthonormal system of eigenfunctions. We already proved that the eigenfunction can be orthonormalized of k, that is, we can write this fx as a series of fk phi k of x, where these phi k's are the orthonormal system of eigenfunctions, and this fk is given by this inner product of fx with phi k. Further, the Fourier coefficients of fx, this part, and the Fourier coefficients of hx are related. So further, the Fourier coefficients of fx are related to the Fourier coefficient of hx by fk is equals to hk upon lambda k. This fk is nothing but inner product of f with phi k. Hk is the inner product of h with phi k, and these lambda k's are the eigenvalues of k. Okay. So let us prove this Fourier theorem, and then we will see how we will use this, how we can use this Fourier theorem, Hilbert-Schmidth theorem for solving the integral equation. So let's do this proof. So first let us prove that fk is equals to hk upon lambda k. So that relation we will prove first. So fk is given by inner product of f with phi k, and this is nothing but kh with phi k, and this will come from here. You can write this f as kh, right? The shorthand notation with what we have seen earlier. Alright. So fk is inner product of f with phi k, and that f can be written as kh with phi k. Then you can take this aside, the operator. So h with k phi k, k is a symmetric kernel, remember that. Then k phi k is nothing but this phi k and lambda k are the eigenvalues and eigenvectors. So it can be written as h with phi k upon lambda k, because since phi k and lambda k are the eigenvectors and eigenvalues, eigenfunctions and eigenvalues respectively, we can write it as k phi k is equals to lambda phi k, and then you can take this lambda k down, or you can write this in the respective form, right? So that this we get here. These lambda k's are the reals, where this is a real symmetric kernel. So 1 upon lambda k inner product of h with phi k. And inner product of h with phi k is nothing but hk. So hk divided by lambda k. And that completes our claim that the Fourier coefficients of fx and the Fourier coefficients of hx are related by fk is equals to hk upon lambda k. So next we have to show that the Fourier this fx can be expanded in terms of the Fourier series. So let us assume the Fourier series. Next the uh, Fourier series representation of fx is, let us write that representation as summation n from 1 to infinity fn phi n of x. These are the eigenfunctions. So fn, this is same as summation n from 1 to infinity. Fn is the relation what we have proved, hn by lambda n. Just now we have proved phi n of x is there. And let us denote this as equation number 2. Now we have to show that this series is absolutely and uniformly convergent. And for that, let us take the sequence of the partial sum. Let us take the partial sum of the given series. So consider the partial sum Consider the sequence of partial sum. Let us take this partial sum summation, this mod of summation k from say n plus 1 to n plus 3 Cauchy's test, if I'm not wrong, hk, then phi k of x divided by lambda k the whole square. Now we have to show that this can be made very arbitrarily small or tends to 0 as this n tends to infinity. Okay, we have to show that this can be made very small. Alright, so this can be, we can use one of the named inequality over here. You check out what is the name of that inequality. This is exercise. So summation k from n plus 1 to n plus p hk square into summation k from n plus 1 to n plus p mod of phi k of x divided by lambda mod of lambda k whole square. Now this is there are suppose say 10 terms, and if you take this to infinity, k from 1 to infinity, then obviously this equation will be less than or equal to that summation. So this will be less than or equals to, we will keep this as it is, summation k from n plus 1 to n plus p hk square, and then this we will write from summation. There are some few terms over here, so we will take all the terms. So summation k from 1 to infinity mod of phi k of x the whole square divided by mod of lambda k the whole square. And then we already proved that this can be made less than or equals to c1 square or c square. In one of the results we have proved that can be made very small. So summation k from n plus 1 to n plus p, we are keeping the same, hk square, and then this can be made, this is less than or equals to c1 square, and this we already stated in one of the results, right, from result. And this, if you see, this h function h is a L2 function. That's what we know. So as, let me write here itself, x H belongs to L2 class, this can be made arbitrary small. This can be made very small, and that means this tends to 0, and this implies series in 2, in equation 2, this implies series in 2 converges absolutely and uniformly. Okay. Now our claim, it converges in mean to fx. Claim series in 2, series in 2, you see the equation number 2, this is a series. So we have to show that this converges in mean, so we can write fx is equals to this series, equals to, here we have not written equal. Okay, so that's a representation. Series in 2 converges in mean to fx. This is our aim now. So let phi n of x, we will take psi, let's take psi. Let sin of x to be this summation k from 1 to n hk by k of x upon lambda k. Let us take this time to be like this. So this implies what will be fx minus sin of x. So this will be equals to fx, we know fx is from equation number 1, fx is integral from this, so it is nothing but kh, this fx can be written as kh. So we can write this fx minus sin of x to be khx minus sin of x is this, so summation n from k from 1 to n hk by k of x divided by lambda k. This is same as written right from here. This is same as kh of x, khx minus summation k from 1 to n. Hk is nothing but h, inner product of h with phi k, and then phi k of x divided by lambda k. And this, if you see, this notation is nothing but the truncated kernel. T n plus 1, we have used the notation for your superscript for truncated kernel, and this entire thing is the definition for truncated kernel for this kh of x. Right? This is truncated kernel. Right? And so if you take mod or norm, we have studied already from the functional analysis, therefore norm of fx minus sin of x the whole square will be equals to norm of k, this truncated kernel, and plus 1 h the whole square. And this norm is same as the inner product of k and plus 1 h with k and plus 1 h. So we can take this as operator that side, so it is h with k and plus 1 k and plus 1 h, and let us write this as inner product of h with k and plus 1, we'll write down here 2 h. Okay, so this we have used we have stated some results, so let us use that result here. The list eigenvalue of kernel k2 n plus 1 is equal to, when you enumerate it, we have found the, when you expanded the kernel as a series, and there we have mentioned that we will arrange them in the ascending order of phi k, phi n, or lambda n, and so on. So from there we can write this as the smallest one is lambda n plus 1 the whole square. Further, again from the result, 1 upon lambda n plus 1 the whole square will be equals to maximum of inner product of h with k2 n plus 1 h inner product divided by inner product of h with h, maximum, and hence this norm will be equals to, and then less than equals to, thus norm of fx minus sin of x the whole square will be equal to this, we got equal to be h k2 n plus 1 h, and this will be less than or equals to inner product h with h upon lambda n plus 1 the whole square, because of the last these things, and this is nothing but the norm of h the whole square divided by lambda n plus 1 the whole square, and this will tend to 0 as n tends to infinity. Why? As we have mentioned that lambda n will tend to infinity as n tends to infinity. So fx minus sin of x the whole square tends to 0. That implies, so also norm of f minus psi by using triangle inequality is less than or equal to norm of f minus sin, because you have taken sin, you have fixed psi, plus norm of sin minus psi. This tends to infinity here, sorry, this tends to 0 here, and this again sin tends to psi, then goes to infinity. So this tends to 0 as n tends to infinity, and this implies f is identically equals to psi. So remember what we have taken psi. So we will say that sin tends to psi. As n goes to infinity, this will go to infinity, and that is equals to psi. This function, right? Ultimately, this is what we wanted to show, and that completes your proof of Hilbert-Schmidth theorem. And let's see some consequences of this, and then in the next video we will see the application part of this. Consequences of Hilbert-Schmidth theorem. We can use this Hilbert-Schmidth theorem for solving the integral equation. Consequences. Now consider the integral equation. The integral equation with symmetric kernel, symmetrical to kernel with symmetric kernel, say y of x is equals to fx plus lambda integral from a to b k xt yt dt. Now suppose that, this is important now, suppose that this lambda is not, okay, we can use this theorem only if this lambda is not the eigenvalue. Suppose that lambda is not the eigenvalue, of the symmetric kernel K x comma t. So assume that this lambda is not the eigenvalue of the symmetric kernel kxt, and that all the eigenvalues and eigenfunctions of kx comma t kernel kxt are known. We know all the eigenvalues and eigenvectors, so eigenfunctions are known, and we arrange them in the way we have discussed earlier. Known and arranged as described earlier. Okay, so we have this equation y of x minus y of x equals to fx. Let us take this fx that side. So now we'll have y of x minus fx is equals to lambda integral a to b k x comma t y of t dt. Let us take as equation number star. Now if you notice, this is left hand side, and then lambda kh or ky is our right hand side. In this case our h is replaced by y. Okay, so this is the form of Hilbert-Schmidth theorem. This is of the form in Hilbert-Schmidth theorem. So let us use the Hilbert-Schmidth theorem. By Hilbert-Schmidth theorem, HST, we can write now remember, we assume that we know the eigenvalues and eigenfunctions. Okay, so we can write y of x, or left hand side the function y of x minus fx as a series summation k from 1 to infinity some constant ck by k of x, where we know this ck is where ck, you compare this with the Hilbert-Schmidth theorem, ck will be equals to inner product of y, we had h with phi k, so h y minus f, right, f with phi k. You see the inner Hilbert-Schmidth theorem, it is these fk's are inner product of f this side with phi k. So our left hand side is nothing but here, in this case in our case y minus f with phi k. So when you open and use the properties of inner products, this will be inner product of y with phi k minus inner product of f with phi k, and this we write it as yk, and this we write it as fk. So this is nothing but yk minus fk. So ck is equals to yk minus fk, and this yk minus fk will be equals to lambda yk upon lambda k. This we will form as ck will be equals to hk upon lambda k. Okay, this ck will be equals to hk upon lambda k, and then this from the Hilbert-Schmidth theorem we will compare, and then we will get yk minus this one will be equals to lambda yk upon lambda k. So when you simplify this further, this will be equals to, simplifying this for yk is equals to lambda k fk divided by lambda k minus lambda. When you simplify this for yk, and by using this you will get ck as lambda upon lambda k minus lambda with fk. Inner product, this is, remember this fk is nothing but the inner product of f with phi k. So when you take this and substitute in star, substitute this in star, we get y of x is equals to fx plus that series summation k from 1 to infinity lambda upon lambda k minus lambda fk, and then we had phi k of x. Right? We have taken this fx that side and then we have done the series. So this is equals to fx. Now here this we can write as a solution, but here we know this f, we know lambda, we know lambda k, lambda phi k's are the eigenfunctions, but we will write what is fk. So this is nothing but fx plus lambda we will take outside, lambda summation k from 1 to infinity. Phi k we know these are the eigenfunctions, phi k of x upon lambda k we know this is the eigenvector, this is the lambda what is given in the integral equation, and our fk also we know. Right? What is fk? Fk is the inner product of f with phi k. So this gives the formula to write the solution of given integral equation. How you will write the solution? The solution is nothing but y of x is equals to fx plus lambda summation k from 1 to infinity. Phi k's we know, so phi k of x upon lambda k minus lambda, and then this fk is nothing but inner product of f with phi k. And how to define this inner product on relative space we already know from the functional analysis. So in the next video we will see one of the example and how to use our Hilbert-Schmidth theorem and when to use the Hilbert-Schmidth theorem to solve the integral equation.